The second half of chapter 1 really deals with how we collect data, how we analyze that data, and how we represent it. And the two ways that we can really collect data are qualitatively and quantitatively. Qualitative data is recorded without numbers and units, just using our senses, like a pink t-shirt or a foul odor. A quantitative data set is data that's recorded with numbers and units, like 10 centimeters or 55 kilograms. Two different terms that we don't want to use interchangeably when we're both in the lab and we're talking about things here in class are mass and weight. The mass of an object is simply just the amount of matter in that object measured in kilograms if we're talking SI units. The mass of an object doesn't change relative to its location. You have to physically take mass out of something. You have to take atoms out of something to make it have less mass. The weight of an object, on the other hand, is the force of gravity pulling on that given mass, measured in newtons. For instance, the weight of the Earth pulling on a mass can be measured as a force. If you take an object and move it up to Mount Everest, you're a little bit further from the center of the Earth, and you would feel less weight, less gravity. So weight is determined by the position of the two objects that are attracted together. Another way to look at this is if you have the same person who has the same mass, right? 63.5 kilograms. You take that person, put them on the moon, put them on Jupiter, put them on the sun. All of these situations would cause the weights to change, but the mass of the person would never change. Two things that we talk about that are connected together are independent variables and dependent variables. The independent variable is the variable that is being altered by the experimenter. It's the variable that causes a change in the other variable that we're studying. The dependent variable is dependent on the other independent variable. It's responding to the changes that are being investigated. So in this very simple example, if we were to adjust the amount of water and to see how that affects plant growth rates, the plant growth rate would be the dependent variable and the amount of water would be the independent variable. Then, if we stick with the same scenario, our control group is the standard of comparison based on the independent variable. So for instance, if I wanted to adjust the amount of water that was being given to these plants, my control group would simply be the group that gets no water to make sure that there isn't something else causing the plants to grow. My constant variables, or my constants, or the other variables that I don't want to influence the experiment. Maybe the number of beans could cause less or more plant growth, so I want to make sure that there's 10 bean seeds in both pots. I want to make sure the material in both pots is the same so it doesn't influence their growth. Those types of things need to be controlled. They need to be constant across all of the experimental groups and control groups because we want to make sure that we're actually establishing a relationship. So if you look at this graph, this is not an experiment that I would expect you or encourage you to run yourself, but statistically speaking, if you were to test your average automobile speed and how far you are over the speed limit versus the cost of the speeding ticket that you would incur, those two things are probably related. You would get a larger fine for speeding a greater speed over the limit. You can control your speed. You can go slower. That's your independent variable. Your independent variable is going to be on your x-axis. Whatever is responding to that change is on your y-axis. A good title for a graph is always your dependent variable versus your independent variable. And that's a good default if you ever are struggling to come up with a title for a graph. This is a really good example for us to talk about experimental design. I want to give you 5 minutes to read through this scenario. I want you to identify the independent variable, the dependent variable, the control group, and 3 variables that should be constants. Take 5 minutes and see if you can do that on your own. My independent variable would be the temperatures, because that is what we are adjusting. That is what the experimenter is changing in this experiment. And the number of fish eggs is the dependent variable, because that's responding to temperature change. My control group should be whatever temperature is closest to room temperature or the normal temperature. So maybe my 20 degrees Celsius group could be my control group. 3 things that I would want to make sure are constants. Dissolved oxygen concentration. We want to make sure that's the same. Maybe lights, make sure that we place them in the same lighting fixture. The pH of the solution, we don't want the pH to be different between the different groups. The species of fish, how can we compare the number of eggs if we're not using the same species of fish? So there's several ways to look at the types of things that we don't want to impact our overall experimental design. When we talk about research and the types of things that we do to investigate the macroscopic and microscopic world, you can really categorize these things into 2 groups. Pure research is done just by curiosity, just by our genuine interest in the scientific question at hand. Like this picture of a black hole that was taken a year or 2 ago. That's such a cool picture. It's interesting. It took a ton of work for us to take a picture of a black hole. But is that going to help you when you wake up tomorrow? Not necessarily. So pure research is generally driven just by natural curiosity, whereas applied research is driven by a problem at hand. Technology is often the solution to that problem, like the smartphone. The smartphone came about because people had a problem. They couldn't check to see what was going on in other people's lives quick enough. Bam, the smartphone. COVID-19, the race to find a vaccine. Vaccines are applied research because it's research designed to fix a problem. I would recommend that you review all of your safety guidelines. I gave you a lab safety contract. These guidelines are in there. The exhaustive list can be found on page 19 in chapter 1 of your textbook, but some of the more common things that I see as being issues, things that are often overlooked. Always use caution and proper equipment when handling hot glassware. Hot glass always looks the same as cool glass. Anytime that you're handling something that's very hot in the lab, the glassware is going to look the same. Always put your hand close to the glassware and see if it's still radiating heat to see if you need rubber hot hands or beaker tongs to actually handle something. Do not return unused chemicals to the stock bottle. Another thing that's often overlooked, and this is more so about contamination, because when you take a container of orange juice and you pour yourself orange juice and you only finish half the glass, you don't pour the orange juice back into the container. That's gross. The same is true about anything that you take out of larger containers in the lab. We don't want it to contaminate everybody else's samples that they're trying to take. The last thing is always slowly add acid to water, not vice versa. And the reason why is if you add an acid to water, the water can absorb that heat from the acid dissolving. If you add water to acid, the amount of heat that is being generated by that acid is only being diluted by a small amount of water at that time, and it can overheat, it can splash, it can bubble. So that's something you should not do. Our next unit is going to be data analysis. So from here, you should have a calculator when you come to class, and we'll talk more about everything involving numbers, units, and everything in between for Chapter 2.